Hey everybody, Jean-Marc here with a lesson on probability density functions. So if you're taking a course in maybe statistics or quantum mechanics or statistical mechanics, this could really come in handy to help you get a intuitive sense of what a probability density function is. So in each slide I'm going to give a verbal explanation, but all the information is also going to be on the slide in terms of text and images. So if you need to go over a part more, just pause it and take your time and read what's on the screen, and that should help. Okay, so we're going to start with a very simple example. Let's say we have there's a college class where there's 139 students in the class, and we're interested in figuring out. We want to get a sense of how old the students are. So we could just list all of their ages like this, and that's not particularly helpful, not too easy to look at. So a nicer way to do this would be to histogram them into a distribution of ages shown here. So here we have a distribution of ages, and when I say histogram, what that means is you take each age and you essentially, the word we use is bin them. So you count how many fall within each bin. So the first bin would be greater than or equal to 17 but less than 18. The next bin is greater than or equal to 18 but less than 19, etc. So we count and we have 4 people that are 17, 13 that are 18, 28 that are 19, etc. So that's where this distribution comes in. And Mathematica has an automatic function that does that for us, so that we can see how many people fall within each age, and we bin them into a histogram like this. So that's an age distribution. Now we can get information from this distribution. So say we want to know the average age of a student in this class, or the mean value. The way we can do this, well, first we could take this list and just add all the numbers up and divide by 139, the total number of students in the class. But another way we could do, if we have this image in front of us, we could do it much more quickly by just taking the number of each students of a particular age multiplied by the age. So we have 4 17-year-olds, 13 18-year-olds, 28 19-year-olds, etc. And we have that on the outside, and then we just divide that whole thing by 139, and that gives us the mean value. And just as a check, Mathematica has a function that will take the mean of any list of data, and just by adding them up and dividing by the number of values there, and we see that it's the same thing. So essentially we just did some very minor algebra to write it a different way here. So that's how we can find the mean. And this all seems very simple and trivial right now, but it's going to really come in handy later when you try and think about a probability distribution or a probability density function. I'll use density and distribution kind of interchangeably. So here we have the distribution adjusted so that now what we have is a probability density function. Specifically, we have a discrete probability density function. So we have the exact same shape. If you notice, the graph is the same shape. The only thing that had to change is that we have to adjust the y-axis. So the y-axis, some sort of scaling went on here. And you can get Mathematica to do it automatically by just putting probability here, and then it knows that you want to scale this with probability. And the way it gets scaled in such a way so that if we were to calculate the area of all these boxes and add them together, we should get 1. And it has to do with something called normalization, which is coming up later in the talk. So, but just know now that we were able to take our distribution of ages and turn it into a probability distribution of ages. So how does this differ? So we didn't do much. We scaled the y-axis, but it's a very different type of set of data here. So when I say it's a probability density function, now what I'm saying is now this describes the probability of walking up to a random student in the class and asking them, how old are you? So that's the experiment we're running. It's not much of an experiment, but it works well for teaching purposes. So you ask a student how old they are, and then this distribution shows the probability of various ages. So now we have our first probability density function, or PDF, for ages. So now let's say we want to find, again, let's say we want to find the mean value that we would measure with our experiment. Or in this case, it's actually known as an expectation value. So if you have some sort of statistical experiment that you run multiple times, and you want to know the average value that you get if you run this experiment a bunch of times, that's known as an expectation value. So the way this is done is you just take the value of interest and then you multiply it by the area of each bar that corresponds to that particular value, that particular outcome. So as far as getting the outcome of someone saying they're 17 years old, we look at this bar right here and we see that the height is 0.028777 and the width for all of these is just 1, right? Because when we set up our bins, so remember I talked about bins and counting how many fall within each bin, we set our bin width to just 1. So if you're 17 here, 18 there, 19 there, so it's simple. So we're just multiplying by 1 for the width for each of these. So if we do that for this entire distribution where we multiply the value we're interested in, so 17 years old, 18 years old, 19 years old, the outcome, multiply the outcome by its probability, or which is also known as its weight. So this is also known as a weighted average or a weighted mean. So we're multiplying each value by its weight. So that's how we do that. And you see we get the same answer for this. So which is what we would expect, right? If we run the experiment a bunch of times with the same group of people, we would expect them to say the same, to get the same average age as if we just take everyone in the room and take their average of their age. So I said something important here. So the weight is the area, not the height. So it's tempting with this particular example to think of the weight of each one as just being the height, right? Which is why I made a point to write multiplied by 1 here. You know, of course, it does nothing to the answer multiplying by 1, but I put that in there because each one of these, it's really the area from 17 to 18 determines the weight of the outcome 17 years old, and the area here of 0.0935, etc. times 1 is the weight of getting 18 years old as an answer. So just to really get this point home, here's an example where I do a histogram with less information in it. So this first histogram, we just counted people by their age. So we set our bin width equal to 1. So we were able to kind of get a more precise reading. So let's say we had a less precise reading where we binned them by 2-year gaps, or 2-year bin widths. So here we have a bin width from 16 to 18, from 18 to 20, from 20 to 22. So these are 2-year bin widths. And in this case, we would do the same process to figure out what the expectation value is. And that is, we multiply the area, which is the weight of each outcome, by the value. So for this one, we have the value 16. So this is from 16 to 18, right? So that the lower limit is 16, and we multiply that by the area of this particular thing, which is bin width 2 times 0.0143885. And we just do that for each one. So you multiply our bin width of 0.2 times the height. And if we do this, you see that we get roughly the same answer. So we lost some precision by using these kind of oversized bins, but nonetheless, our average value, or our expectation value, didn't change too much. So it went from like around 20.2 to around 19.7. And that's due to loss of precision. And this is also, also goes to show like what's going on with discrete probability density functions, where we have some kind of limitations on accuracy. And we're going to get into continuous ones soon. So now, with this kind of explanation, we can rigorously define what an expectation value is for a discrete probability distribution. So here it is. You multiply x, which is the value we give it, right? So with any function, you give a value, you get a value, right? So if the function's y equals x squared, you give it a 2, it returns a 4, right? It just squares whatever you give you. So same thing here is we have some function that we give it an x and it returns some value, which is the height of the function, right? So we give it each particular value, so in this case x's are the ages, and then f of x is the height of that function, that's what it returns, and then you multiply that by the min width. And you add these up, and that will give you the expectation value. So this is for all cases for your discrete probability distribution. And again, I have it written down here so you don't forget. So here's our definition of the expectation value for a discrete probability distribution. Now, you can get other information from a probability density function other than just say a mean. So let's say, just for another example, let's say that we want to figure out the probability that if we ask a random person their age, that it's going to be somewhere between, let's say, greater than or equal to 17 and less than 20. So let's say, so that means we want someone in this range. So it turns out the way you do this is simply by adding up the areas of the range that we're interested in. So it's just going to be this height times 1 plus this height times 1 plus this height times 1. And that's what we have here. And if we look at our value here, we see that there's about a 32% chance that if we pick a random person in the room, their age is going to be greater than or equal to 17 and less than 20. So if we write this formally, we get this definition at the bottom here. So the probability that x is between a and b is going to be the sum from a to b of the function, so the height, times each the height of each value times its bin width. So essentially it's just we're finding the area under this jagged curve here. And hopefully when I say area under curve, that makes you think about an integral. Because when we get into continuous ones, you're going to see that this transitions into an integral. Okay, so it's just the area within the region of interest is probability of finding something in there. So now that we know how to find the area, now that we know how to find the probability of a value falling between some particular area, now we can talk about normalization, which I kind of hinted at earlier. So if a function, so any probability density function must be normalized for it to be meaningful. And what I mean by normalized is it's actually pretty common sense if you look at the distribution. So if we look at this thing, every single person whose age we asked was there was no one younger than 17 and there was no one older than 23, right? So that means that if we look at this entire area here, that means if I use this equation down here and I add up all these areas of someone between, say, I could say 16 to 30, because we're going to get zeros up here, right? And for 16-year-olds, we don't have anyone who's 16, right? So there's not going to be anyone in that bin. So if I were to add all of those up, then that covers every possible age. So then the probability that if I ask someone their age from this group, that it falls between 17 and 23, then it should be 100% every time, because we know that there's no one older than that, no one older than 23, and there's no one younger than 17. So that needs to be 1. If that's not 1, there's something wrong with our probability density function. So that's what normalization is. So if I add all of these heights times their widths, that's what we have right here. So if we add them all up, we find that we get just shy of 1. And so the reason for that is just a rounding error, because this is a numerical example. But nonetheless, we can say that this is normalized, at least within a certain margin of error. So that's what normalization is. Okay, so now we can start talking about what a continuous probability density function is. So we started with a discrete one because that's a little easier to kind of wrap your head around, because I can talk about something concrete like a group of students and their ages. Whereas a discrete one, so there were hard cutoffs between the ages. So our function had that jagged shape due to the histogram type function. So it had a jagged shape, but you can actually define continuous probability density functions that are much more precise. And remember how when we use this particular probability density function where we use larger bins, it was less precise, and this is more precise, this is less precise. So you can imagine if you can get a smooth one, you can get even higher precision. So that's the idea with continuous probability density functions. So how do we treat them mathematically? So as we mentioned with getting the expectation value, let's look at that as an example. For taking expectation value, we had this sum here, and it was just the value we put in, the function, the height of the function that comes back out from giving it that variable or that particular outcome multiplied by the bin width, right? So it was essentially the weight of each possibility multiplied by the possibility. So we can do the same thing. If you remember from defining what an integral is the area under a curve, right? And your calculus book may have had an example where you have something like this, where you're multiplying the length times the width of a bunch of rectangles underneath a curve, much like the histograms we showed. But then you take the limit as the bin width goes to approaches 0. So that's kind of what's going on with an integral, and it's really no different here. So we have the same thing going on, whereas now we have the outcome multiplied by its weight, which is the function integrated over dx between whatever range you're interested in. So hopefully that's clear how we transition from this to this. It's essentially that same limit that defines an integral. So now let's talk about normalizability. So the requirement for any function to be a PDF or a probability density function is that it must be normalizable. It doesn't necessarily have to be normalized right out of the gate, but it has to be able to be normalized. And what this means is if you integrate it over all space, it has to give you a finite value. So for example, the function y equals x squared, if we integrate that over all space, it doesn't converge to any value. It's infinite, right? Because it just keeps growing. So y equals x squared does not work as a probability density function. But let's say we have some function p of x that if we take its integral gives us a constant value c. And that's after integrating over all space. So we can integrate from negative infinity to infinity, we get a constant. So that means that this function is normalizable. So then if we want to normalize p of x, all we have to do is multiply it by 1 over c, this value here. Because now if we look at this expression at the bottom here, this integral should give us c, and then if you multiply it by 1 over c, that gives you 1. So this value, this function right here with that normalization constant in front of it is a normalized probability density function, so we can use it. So let's talk about an example of a probability density function, a continuous one. So this is one of the most popular and useful types of probability density function called the Gaussian distribution. So if you want to get a feel for just how important it is, look up the central limit theorem. It's and if that doesn't convince you how important this distribution is, I don't know what will. So if we look at this function here, this is the Gaussian. This is the form of the Gaussian distribution. So we have x is our variable, and we have two parameters in there as well. Pi is just a constant, it's pi. And then we have sigma, and we have mu, and then sigma appears again down here. So sigma is standard deviation, and mu is the mean value. So we can define where we want the mean and the standard deviation of this distribution to be. So right here I have defined a function where I can vary the value of sigma at the top here, and mu is the second slider. So if I change the value of mu, you see our distribution just slides from left to right because I'm changing the mean value. And just looking at this distribution intuitively and how we've been looking at our discrete distributions, we know that the mean value creeps up somewhere around the peak typically. So looking at this, it doesn't surprise us that now we've increased the mean value, now we've put it somewhere around 0, right? Now standard deviation, if you've heard of standard deviation, you know that it has something to do with the thickness or the width of a distribution, right? So if I increase the standard deviation, this distribution just broadens out. So if I keep it small, then if we pull a random number from this distribution, we're going to expect it to be most likely somewhere between negative 0.5 and 0.5, right? Just looking at our axis here, here's negative 1, here's 1, and we would not expect to get an answer of, say, negative 1 at all. So that's how standard deviation works on the Gaussian distribution. So now let's take this a step further here. Let's create one particular Gaussian distribution, and we're going to creatively call it Gaussian. So that's right here. So we've set mu equal to 0 and sigma equal to 1. So this is our distribution right here. And here's a plot so you can see what it looks like. So now we're going to take this distribution, and Mathematica has a function called random variate that allows you to define some sort of distribution and then pull numbers from it. So this is equivalent to when we talked about our little our lame little experiment of walking up to a student and asking how old they are. So this is the same idea, except I'm asking Mathematica. I said give me a random number from this Gaussian distribution that I've defined here. So each time it just gives me a random number. So it's like walking up to a random student and asking their age. So we're much more likely to get a value that's, say, between negative 1 and 1. If we got a 3, we'd be pretty surprised, right? But it could happen. So essentially what we do is we define this list of variables here, and this list has 1 million random variables in it. So it's as if I asked Mathematica 1 million times, give me a random number from this distribution. So that's what this data set is Gauss data. So if I plot a histogram of it, superimposed on the distribution function, the PDF, the Gaussian PDF that we've defined, we see that they match each other quite well. So that's this function right here. The scaling is a little different, so it looks a little thinner, but it's the same function. And right under it is the histogram. So we see that they match each other quite well. And I've set the bin width equal to 0.5 here. So now the next step, we're going to do a couple operations using both our continuous Gaussian function and our discrete approximation here. So essentially what I've done is we're comparing two Gaussian distributions. One is the continuous Gaussian distribution, which is just the smooth function here, which is, should give us the perfect answers. And then we have these this approximation here using the histograms, which is like our discrete distribution, but it's still a Gaussian one because all of our discrete distribution came from pulling numbers from this continuous Gaussian distribution. So that's what we're comparing here. So let's see. So first of all, let's say we're interested in knowing, let's say I want to know what's the probability that I'm going to get a number less than 0. What's the probability of getting a negative number? So looking at our shape here, intuitively, if we remember from the equation, let's see, if we wanted to know, here it is, if we want to know the probability of some value being within a certain range, this is how you do it, right? You multiply the bin width times the height of the function for each one of those values within the range, which again is just the area under the curve, right? Because the height is f of x and the width is your bin width. So all we need is the area under the curve is what we can get within the region of interest. So if our region of interest is negative, we want to know what's the probability of getting a negative number. We could say it's from the region from negative infinity to 0. But this thing dies out pretty quickly, so we could probably even just say something like negative 5 to 0 and still get the same answer. So we could do this two ways. So we want the area underneath this curve. So in the continuous sense, we just take an integral. So first we do that. So if we integrate our function Gaussian from negative 5 to 0, and again this could have been negative infinity to 0, we get 0.5. Which makes sense. Looking at this thing, we would expect a 50% chance of a negative number. And then the same thing should work if we just take the area of each of these rectangles and add them up. And sure enough, that works as well. So here's all the heights, and then we just multiply it by the bin width at the end. And it's slightly different, but that's really only because of rounding issues. and it is a numerical approximation. It's fairly well sampled because we did take 1,000,000 numbers, right? So if with statistical distributions like this, if I would only take, say, like 5 values, it could be not representative at all, right? But with statistical things, the better sampled it is, the more accurate things are going to reflect the distribution that they're coming from. But I digress. So let's try another one. So the expectation value, just eyeballing this thing, we should figure it should be about 0, right, in the middle of this. So expectation value for continuous functions is just the x times f of x, and it's an integral, right? So this is, that's this right here. Remember, we just take x times f of x, or the integral of x times f of x gives us the expectation value. So if we look, that's exactly what I did here. X times our function Gaussian, and we integrate it from -4 to 4, and we get exactly 0 as our expectation value. So if that's what we expect to get, if that's the mean value that we get, then we could say, like, okay, so if I ran this experiment 100 times, got a million different random variables, its average number should be 0. And that's what we do here by using the mean function. And it's slightly less than 0. But nonetheless, it's very, very small. It's practically 0, and again, this is due to the limits of it being a finite system, and also to perhaps some rounding errors. So one other thing we can take is variance. So as I mentioned, the square root of variance is standard deviation, right? So that's how it relates here, and variance is taken very similar to the way we take the expectation value, except instead of x times our function, it's x squared times our function, and that will give us variance. So with this Gaussian distribution, the way we defined it, we were able to choose what we wanted standard deviation to be, right? We chose 1. So 1 squared is 1, so we expect our variance to be 1 as well. And we look, and it basically is, right? It's slightly less due to some sort of numerical reason. And let's see here. So in the same way, if we ran our experiment a bunch of times and ask our function for a random number 1,000,000 times, we would expect the variance of that distribution to be very close to 1 as well. And sure enough, here it is, just slightly over 1. So hopefully this was helpful. Please subscribe. Thanks for watching. And if share it with anyone who you think could benefit from it. All right, thanks a lot.